Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Numerical Approximations of, and in this lecture we have a rare event. The calculators are in fact encouraged. Some elementary functions simply do not have antiderivatives, and so you can't find antiderivatives of any of these functions listed here. So if you need to evaluate a definite integral having those, but you can't find the antiderivative, the fundamental theorem of calculus is still true but can't be applied. So in this case it's easier to resort to an approximation technique, and that's what we're talking about today. You certainly could use the midpoint rule, and here we've got a red function that we want to approximate, and so what we're going to have is 1, 2, 3, 4, 5, 6 rectangles that will approximate, and we'll use the height of the rectangle to be the value of the function at the midpoints of these equally spaced intervals, and the width is always going to be this delta x is b minus a over n, and we partitioned this interval into those pieces. So the definite integral from a to b f of x dx is approximately equal to delta x, which is the width times the height. For each of those we add them up, and we can factor out delta x. So that is a general midpoint rule. We also could slice them into and approximate the area with what we call trapezoids. Now here you have vertical lines, those are the parallel sides of the trapezoid, and then we're going to get the areas of this, and so these are going to be the bases, and the heights are going to be the distance between these, which we're taking again to be b minus a over 2. So here we have 4 trapezoids. Now notice when we take the area of this trapezoid, we will have these two bases and the height. But when we go to the next one, we'll also have this base is repeated, and a new base, and then the height. And over here, we will have this base is repeated twice, but this one is only once. You'll see that in the formula. Okay, so if we're going to approximate a definite integral using n trapezoids, what you do is slice the interval into equal pieces where b minus a over n is delta x. Those are the values you chose. You start at a and you end at b, and then you look at each trapezoid. Now the area of a trapezoid is 1/2 the sum of the bases times the height, and you can see that this is what we get. So then if we add all those areas together, what happens is, notice that I can factor out the 2 from here, and that gives you b minus a all over 2n, and we have all of these. But notice that except for the first one and the last one, these are all repeated, so it is 2 times that. And so when we let n go to infinity, this can be calculated to approximate the definite integral. Okay, so that is the trapezoidal rule. Here's a statement of it. So if f is continuous on AB, the trapezoidal rule for approximating the integral from a to b f of x dx is given by this formula. Moreover, as n tends to infinity, the right-hand side approaches the definite integral from a to b of f of x dx. This means that you can make this as good as you want. And I observe in the note that the coefficients follow this pattern: 1, a bunch of 2's, and then a 1 again. It is interesting to compare the trapezoidal rule and the midpoint rule. Here we're taking f of the average, and here we're taking the average of the f's. These things become more accurate as n increases. Now we have another thing called Simpsons Rule, and there is a little theorem that helps us calculate the Simpsons Rule, and that says if you have a parabolic sector, then the area under the parabola is going to be this expression. And what you do is you just do a rote calculation, plug in the numbers and subtract, and do some fancy algebra, factoring some things out and collecting terms, and we do have this expression is true. And we are going to use this when we look at the proof of the Simpson theorem in a minute. But what the Simpson theorem says is, instead of just drawing a line there, let's use 3 consecutive points, and let's put a parabolic curve through them, and the idea is that might be a better approximation. Now think about this. Whenever you draw this parabola using 3 points, this is used, but then when you draw the next parabola using 3 points, that is used again. And so some of these are being used more than others. And so if you think about that, you'll see what happens in this. So if we develop Simpson's rule for approximating a definite integral, you partition this into n equally width intervals, like that, and we approximate f by p. So parabolic. So between x0 and x2, remember we use x0, x1, and x2. That's approximately the integral from x0 to x2 of the parabolic approximation. And now I use that theorem that we just proved, and that says that this little piece is going to be b minus a over 3 to the n. You get f of x0 for f of x1 and then f of x2. But then when I start adding these together, I'm going to get 4 for the middle one, but I'm going to get 2 for the endpoints over here. So that leads us to Simpson's rule. So if f is a continuous function on the interval ab and n is an even integer, and it must be even for this to work, Simpson's rule for approximating the definite integral from a to b f of x dx is, now this b minus a over 3n was common everywhere, so what you see is that whenever you put those together, you'll have 2 of these because it appears twice, but you'll always get 4 for the middle term. Moreover, as n tends to infinity, the right-hand side approaches the value of the integral. That means you can make this as close an approximation as you can. And in my note, I observed that the coefficients in Simpson's rule have the following pattern. They go 1, 4, 2. You're alternating 4s and 2s till we get back to 1 again at the end point. So here's a problem using n equal 4 and all 3 rules, the midpoint rule, Simpson's rule, and trapezoidal rule, approximate the value of this integral, the integral from 0 to 2 e to the x squared dx. There is no antiderivative for this. You know what to do. And we'll see how you do when we reach